Alright, so far we have learned a lot of reactions that a benzene ring would undergo and order of reactivity, whether they are activating, deactivating, and which substituent we need to put first if you are going to do a synthesis. So we learned that. So now we're going to learn another important reaction where we can add different nucleophiles on the benzene ring by making this Arenediazonium salt. So this salt has many advantages. Okay, so let's see how to synthesize that, and also how to synthesize substituted benzenes using this Arenediazonium salt. So this is the arene part, and this is the diazonium salt. Certain nucleophiles can substitute for the diazonium group. So when you make this group, diazonium group, by different nucleophiles can be added onto the benzene ring, because nucleophile can substitute this group. Okay, excuse me. For example, benzene diazonium chloride with a nucleophile add onto the benzene ring. The feasibility of this reaction is the generation of the nitrogen gas when you do the nucleophilic addition. Not the nucleophilic addition, it's a substitution. It's not an addition, it's a substitution. Okay, sorry about that. So the nitrogen loses as a small stable gaseous molecule. So that is what drive the reaction forward. Okay, how do we synthesize this? Normally diazonium salt is synthesized using aniline. Okay, aniline is this molecule that you are looking at, benzene with the NH2 group. We use these reagents, sodium nitrite and hydrochloric acid, together at 0 degrees Celsius. So when you do mix aniline with this reagent, you can form the diazonium salt. And then as soon as it's been formed, you have to use it immediately. Okay, otherwise it can break down. So the reactions, these reactions that undergo or substitute the diazonium group, we call this class of reactions as Sand-Meyer reactions. Sand-Meyer reactions. Now, for example, if you want to put a bromine on the benzene ring, you take the diazonium salt and you react with copper bromide. Copper 1 bromide. So then you can have the bromobenzene plus nitrogen. React diazonium salt with copper chloride, you can get the chlorobenzene. And you can also see it can have some other groups on the benzene ring as well. So this one again, diazonium salt react with copper cyanide, so we can have a cyanobenzene. So the Sand-Meyer reaction can be a useful alternative for halogenation. Okay, remember we had sometimes some groups deactivate the benzene ring towards halogenation, so we can use this diazonium salt for the halogenation. Chlorination of ethyl benzene leads to a mixture of ortho and para isomers. Let's say you have ethyl benzene, you add chlorine with iron chloride, you can have the ortho position chlorinated as well as para position chlorinated. But if you use a Sand-Meyer reaction, it only gives us the para product. So basically you start with NH2 group over here, para to the ethyl benzene. Then you react this with sodium nitrite and hydrochloric acid at 0 degrees Celsius to make the diazonium salt. And when this being reacted with copper chloride, you can get the para product. Okay. Another one, when you use diazonium salt with potassium iodide, you can put an iodo group. And then to form a fluoride, you can use HbF4 complex. So then this group will be replaced with the fluorine, so fluorobenzene. Excuse me. Fluorides and alkyl iodides can be made from arene diazonium salts. And then the phenols. also can be made from Arenediazonium salts. You see the advantage? There are so many different reactions that we can do. So the diazonium salt, you heat it with acid. So then this will replace with OH, can form phenol. And then if you use copper oxide with copper nitrate and water, copper 1 oxide and copper 2 nitrate can be added to get a higher yield. For the same reaction, if you add these reagents, you can get the same product as if you get from here, but it would be higher yield. Okay, so both of these reagents can be used to achieve or convert diazonium salt to alcohol group, meaning a phenol. And if you want to replace the diazonium group with a hydrogen, what do we need to do? You need to add phosphoric acid. Let's say you want to make this compound, a tribromobenzene, 1,3,5-tribromobenzene. But we know bromine is orthopara director, but these are meta to each other. How do we achieve it? So you can start with aniline, and aniline is a activator, and this is the orthopara director. So when you add bromine and heat, you will see aniline, both ortho positions and the para positions will be brominated, right? So, and then you make the diazonium salt, NH2 convert to N2 bromide using sodium nitrite and HBr. And then when you heat the diazonium salt with H3PO2 phosphoric acid, we can replace this diazonium group with hydrogen. So that gives us 1,3,5-tribromobenzene. Okay. Okay, so retrosynthetic analysis. Let's say you want to make this molecule from benzene. Remember, the retrosynthesis is you're going backwards, starting from the product that you want at the end, and you go backwards and see how can we come forward. Okay, so synthesis of meta-dibromobenzene from benzene. It requires a Sandmeyer reaction. Remember, the Sandmeyer reaction is excuse me, diazonium salt reacting with different reagents. So this is what you want. Okay, so these are meta to each other. So we can consider this as excuse me, having one bromine already in one position, and then the other bromine position having the diazonium salt. Okay, so how do we make diazonium salt? We can consider it coming from a nitro group. Now this needs to be NH2 here. There is a typo. This group, is it? Let's see. Bromide. I would say something wrong here. Benzene, the nitration, bromine, and not why they do not put this group in the middle. Anyway, they have skipped this part over here. That's what I got a little confused. Okay, because the diazonium salt needs to come from NH2 group, which is not shown here. But we can make NH2 group from nitrobenzene. That's what we are seeing over here. We can get to the diazonium salt from the nitro group. Okay, and then nitro is a meta director. Okay, so if you have the nitrobenzene, then you can add a bromine to the meta position of the nitro group. So this can be achieved from this group, and then we know how to nitrate a benzene ring. Okay, so starting from benzene, how do we go forward? So this is your benzene. You do the nitration with nitric acid and sulfuric acid. Nitration will give, adding NO2 any position of the benzene ring. And then you add a bromine with iron bromide. So nitro is a meta director, so the bromine will add on to the meta position to the nitro group. And then we can convert a nitro group to aniline or NH2 by using hydrogen, palladium, carbon. Okay, reductive amination. Nitro group will become NH2. Hydrogenation. NO2 will become NH2. And then to the NH2 group, when you add sodium nitrite HBr at 0 degrees Celsius, condition for formation of the nitrosonium ion, diazonium salt. And then this will give you this compound. Now we need to turn this into a bromo group by using copper bromide sandwire reaction. You can replace the diazonium salt to bromine. Okay, so that gives us meta-dibromobenzene. Another one. Arene diazonium ion react as an electrophile with highly activated rings. Now let's see, OH is a highly activated ring, phenol, because OH is a activating group through the resonance. Now this is the diazonium, arene diazonium ion. So these can react together to give you this molecule. So what's happening here? The para position. So this carbon adds on to this nitrogen here. Now this can act as a electrophile, forming an azo linkage. Okay, we call this as a azobenzene. The product of the reaction is a azo compound. NN linkage is called an azo linkage. Here, let's look at the mechanism, how it happens. The mechanism, highly activated ring. So in this molecule, you have alkylated nitrogen, a tertiary nitrogen group over here. That is also highly activating, and which is over here what we have is OH. They both are strong activators. Okay. So basically, since this is a bulky group, so it will go from the para position, ortho para directors. So para position acting as our nucleophile. So this is the electrophile with the positive charge attached to this nitrogen. Triple bond now will become a double bond. And then the pi bond breaks up and gives its electron to this nitrogen. Okay. That will give us this intermediate where, so this is our molecule here. This carbon now adds on to this nitrogen. Now you have only 2 bonds and then the rest. Okay, so you will make this intermediate. So we are missing one more step here. After the double bond goes here, this would become a lone pair right there, that lone pair, and then one more resonance structure, and then the base will take up this hydrogen and regenerate the aromaticity, okay, to give you this azo di. Electrophile adds to the benzene ring. A base in the solution removes a proton from the carbon that formed the bond with the electrophile. Don't have to worry about the mechanism. We are missing one step over here. But remember, when you have an active group like alcohol, right, OH group, and with the diazonium salt, you can have an azo linkage. So basically, mostly it can happen with ortho and para position both, but the para position would be least sterically hindered. So you can form a bond. This carbon will be bound to this nitrogen, and will end up having an azo linkage. Okay, and this is a compound. This particular one is a prodrug, prontosil. You see the azo part over here. It's a prodrug, a compound that becomes an active drug only after it undergoes a reaction in the body. Okay, So far we learnt about electrophilic aromatic substitution, meaning benzene ring act as a nucleophile, right? And the electrophiles adds to the benzene ring. Now let's see if we can have a nucleophilic aromatic substitution on the benzene ring. We have a bromine. So we have seen in our SN1, SN2 reaction, bromide is a good leaving group. You can have the nucleophile comes in and leave the leaving group. But here it is a sp2 carbon is what we have here. Normally with sp2 carbon, nucleophilic substitution does not take place. Nucleophile is repelled by the pi electron cloud. Nucleophile is also something electron rich. Benzene ring is also something electron rich. So they try to repel each other. So aryl halides do not react with nucleophiles because the nucleophile is repelled by the pi electron cloud. So that is why normally benzene ring does not undergo nucleophilic substitution. But there are ways that we can achieve this nucleophilic aromatic substitution. For example, if we can lessen, meaning reduce the electron density in the benzene ring, so it will lose its ability to react as a nucleophile. How can we make the benzene ring less electron denser? By putting groups that would withdraw electrons from the benzene ring. And that can be done by deactivating group like nitro group, right? So here you have a 1 nitro group, 2 nitro group, 3 nitro group. So the more nitro group you have in the benzene ring, the more electrons would be withdrawn from the benzene ring, and then it will lose its ability to act as a nucleophile. So at that conditions we can do a nucleophilic substitution on the benzene ring. Okay, let's say this is para-nitro group. Nitro group is para to the chlorine. So you heat this up with hydroxide at 100 degrees Celsius. Then second step, you add hydrochloric acid. So now hydroxide, since there is less electron density in the benzene ring, this can act as a nucleophile and then substitute for the chlorine. Okay, so we have to heat for 160 degrees Celsius because we have only 1 nitro group. But if you have 2 nitro groups, notice that the temperature reduces. So we can achieve the same at a lower temperature, 100 degrees Celsius. So you do the nucleophilic substitution. Hydroxide attack the carbon and then leave chlorine and substitute with hydroxy group, OH group. And when you have 3 groups, we can do a little above the room temperature, 40 degrees Celsius, because now it's even more deactivated. So the chloride is substituted with hydroxide. Nucleophilic aromatic substitution can occur if a strongly electron withdrawing group is ortho or para to the group being substituted. And this is how the nitro group withdraw electrons from the benzene ring. The mechanism for nucleophilic aromatic substitution. So let's say you have a nitro group and then this is your nucleophile. It attacks the carbon. And then the first thing is not losing this leaving group, but since it has a pi bond, it's always the pi bond breaks. So this is a sigma. It doesn't break sigma bond first, so the pi bond will break and give its electron to this carbon. It will become now negatively charged. The incoming nucleophile will stay attached to this carbon. So the leaving group and the nucleophile both on this carbon, so you have a negative charge right there. And then we can do a resonance. So according to the resonance, the negative charge will be here right next to the nitrogen. And this negative charge, the electron that generated, will be going to be away from the benzene ring now because the nitro takes that electrons away from the benzene ring. You see here through the resonance, it goes to these 2 oxygens. Okay. You can draw the pi bond over here as well. So there are 2 resonance structures that you can draw. And then we can continue the resonance again. Once you make this resonance structure, it can again go back to the resonance, forming the pi bond, breaking the pi bond and giving the negative charge on this carbon. and then regenerate the aromaticity, and you leave the leaving group. Okay, so this is with one nitro group. Imagine if you have two more nitro groups at these positions where we generate negative charge. Here and here, there are nitro groups to remove the electron density away from the benzene, making it easier for the nucleophilic substitution to take place. Nucleophile attacks the carbon bonded to the leaving group. The leaving group is eliminated. Why the electron withdrawing groups must be ortho or para to the site of attack. So the hydroxide attack, so this, why the electron withdrawing group, which is a nitro group, need to be ortho or para, because we generate that the negative charge right on ortho and para positions. So having nitro group attached onto the places where we generate the negative charge will directly withdraw electrons from the benzene ring, right? So like that, with the resonance, so it's away from the benzene ring when the nitro group is ortho and para. You see the resonance? Hydroxide attack to this carbon, pi bond breaks, forms another pi bond here, this goes there, and then it all the way to this oxygen. That happens when it is in the para position or in the ortho position, like this. It has a nice flow of conjugation and then the resonance. Electrons are delocalized onto the nitro group. Electrons can be delocalized onto ortho and para substituents, cannot be delocalized onto meta substituents. If they were in the meta position, you see it cannot do that. Now, nucleophilic aromatic substitution reactions on this molecule, you are going to substitute methoxy group with fluoride. We have one nitro group, so that will facilitate the nucleophilic substitution. You react this molecule with methoxide, so then nucleophilic substitution will take place. We can add the methoxy group right there. Okay. And on this one, you have ethylamine as our nucleophile. You heat it, you have two nitro groups, so the bromine will be substituted with ethylamine group. Nitrogen would be the place of attachment, and then when you add another base, it will remove the excess hydrogen and make the product, substitution product, nucleophilic substituted product. So the nucleophile also must be stronger base than the leaving group. Okay. So that concludes our reactions with benzene ring. We learned a lot of aromatic chemistry in this chapter. Lots of new kind of reactions also. So it was an exciting chapter too. Okay then, bye for now.